first presentation will be by Anindya. He was in undergrad geometry and he will talk about pi, history of pi. Thank you.
Thank you, sir.
After the talk.
Okay, sir. So welcome everyone. So today I am going to discuss some few aspects from where the number pi came and how it has evolved till years and what is the historical facts related to this beautiful number. So let's start. And so if we imagine the set of real numbers like the dark sky and the stars as the rational numbers, so we can think of pi though it is not a rational number, but among those stars the number pi is also very unique in its own way, that till almost 4,000 years we are trying to know the number in closer proximity, but still we don't know the actual value of it. Like we are trying to approximate and we are trying to know the number in closer proximity till date. So it is very unique and it's very challenging also to characterize all the properties of this number. Okay. The history began like from the ancient Babylonians. They calculated the area. We know that the area of a circle, it comes as pi into r square. So first they calculated the area of a circle by taking 3 times the square of its radius. So it became, they found the area as 3 into r square, as they found the area as 3 into r square with some fixed radius r. So they got the first value of pi as 3, which is the area of that particular circle, which they constructed with the radius r. So that was the first attempt, more or less, to know the value of pi. And then one Babylonian tablet we get, it's a kind of book. It was around 1900 to 1680 before Christ. It indicates that we can get a more closer approximation, like we can get the value of 3.125 for pi, which is a little closer approximation of this number. Yes, sir.
So was it the area of circle was taken to be 3 r square, or it was set pi r square where pi can be taken around?
They fixed the radius and they calculated the area. It came 3 into r square. Yeah.
Pi r square appeared later.
Yeah, pi r square appeared later. So I was just yes. So then the next text we find that it's Papyrus. That gave us insight about the mathematicians of ancient Egypt. They calculated the area of a circle by a formula which gave the approximation that is also a bit closer, 3.1605 of pi. That's they calculated by the formula which they found in their tablet. Okay. And now they were trying to calculate or approximate this number in terms of the area of a circle. Now the actual calculation, analytically, to derive the value of pi, the approximation started. The Archimedes in almost 287 212 before Christ, one of the greatest mathematicians, he tried to approximate the area of a circle using the polygons. Like polygons, if we inscribe some polygons inside a circle, and if we circumscribe the polygon, and we know the area of polygons through the area of triangles. If we add the area of triangles, then we can calculate the areas of polygons. And if we find out the partition, then we are getting closer to the area of the circle. So he made this approach. I have tried to get the picture for n equal to 4, n equal to 5, and then n equal to 8. And if we find out the partition, then we are going more closer towards the area of the circle. I think this, I try to relate it very later in Riemann integration. What we try to approximate the area under the curve using the rectangles. We find out the partition and we go closer to the area of the circle. I think this idea resembles Riemann's idea of. Yes, sir? Yeah, first I think this idea is first. Later Riemann approximated, and his approximation shows that he got the area between 3 by 7 and 22 by 7. So a similar approach was made by a Chinese mathematician, Zhu. He was not familiar with the work of Archimedes, but because of his book has been lost, little of his work is known to us. He calculated the ratio of the circumference of a circle to its diameter to be 355 by 113. That is one of the definitions of pi, that it is a universal constant for a circle of the circumference to its diameter. That if I have a class of objects, I can attach an invariant to that. That is, if I have circles, for each circle this ratio is constant, and that we denote as pi. So he calculated this ratio. In the light of that definition, we can think of that it is like the area value of one of the attempts to calculate the area of pi. And in the 18th century, some French mathematician Buffon, he used probability to calculate the area of pi, and that is a famous problem, Buffon needle problem, that in a circle, if I drop a needle in which area it moves, like I exactly forgot the exact process, but it's a famous problem he used to calculate the area and try to approximate the value of pi again. Some series approximations, like in 14th century, Madhava found two infinite series. The first series was based on 4 in tan inverse 1, that is famous as Madhava-Leibniz series, and if then pi equal to 4 into 1 minus 1 by 3 plus 1 by 5 minus, like if I take the series expression of arc tan x, that is x minus x cubed by 3 plus x cubed by 5, I put 1, then I am getting 1 minus 1 by 3 plus 1 by 5 minus 1 by 7. And if I multiply 4, then I am getting the approximation of pi with that. And other was based on tan inverse 1 by 3. And I can put that same again in tan inverse x, x minus x cubed by 3. So I am putting 1 by root 3, that this expression is coming. This is also another way he tried to approximate the value of pi. In 1656, in very recent days, John Wallis published this product, infinite product, that is pi by 2, the value of pi by 2. He calculated, that is 4n square by 4n square minus 1. He showed that this converges to pi by 2, this series. In 1910, Ramanujan found some series, actually not one, he found several series which converges rapidly towards pi, but the expression is very long, so I haven't written the expression in my slide. And now in recent day mathematics, the number has played a huge role. It has occurred in many mathematical expressions like the values of Riemann zeta function, and in some partitions, Pn, in some expressions. Yes. Yes, the number. Yes, the number pi has played a huge role. Yes, I should have written that. And many interesting properties like irrationality, transcendence, etc. Those have been proved regarding pi. We hope to discover more and make the life of pi longer.
Any questions to Anindya?
Yes, sir.
Any questions? So, yeah.
Yeah.
So, the Madhava series that is,
Yeah.
So like what is the
Yeah, in the first series, uh, tan inverse x, it is arc tan x. It converges for all real numbers. This is expression. And now if I put 1, so I get arc tan 1, it's tan inverse 1, 1 minus 1 by 3 plus 1 by 5 plus minus 1 by 7. And if I multiply 4 with it, he proved that this series converges to pi. And in the next step, he took the base of tan inverse 1 by root 3, that is, if I put here 1 by root 3, then so same thing, you are getting that 5 into 3 cube, 3 into 3 square, and he proved that if I multiplied it with root 12, then it will converge to pi.
How do we prove that it goes to pi?
That is, I think, I don't know the proof now. That will be
Proof we have tried to avoid. Proof
Yeah.
can be an indefinite.
yeah.
Definitely I will explain.
So I will try.
Any other question? So, is it possible to make a wireless product using the two series?
Hmm?
Is it possible to make a wireless
Wester's product, term by term product. Cauchy-Wester's product you are talking about?
What is product that?
Oh, Wells product. Proof.
No, it would be possible to get them using two series, right? Because there is no generation.
Yeah. That also converges. That product, that also converges to pi by 2. Ramanujan's idea was it converges rapidly to pi. Ramanujan approximated. Yeah. No. Because in the last series, every term is rational number. Root 12 is not rational. Root 12 is not rational. It is irrational. So it is not possible.
Okay, thank you, Anindya.
Thank you.
There will be pause.
Yeah, class of circles. Two-dimensional polygon. Polygons.
N-gons,
Regular n-gons.
Anindya is asking that suppose you take 5
Yes.
similar to circle, you have a circle, you have pi, is there some number associated to 5 and 6?
Like 5, but actually the definition of one of the definition of pi is that it is constant as the ratio of circumference and diameter.
There are some such
Yeah.
numbers.
Yeah.
I also
Some,
know.
yeah, maybe,
There are some such numbers.
maybe,
But it
but
may not be like if any need to divide it by something.
yeah. Huh.
Yeah, so she is saying that see, for maybe
Yeah.
what I can understand, for each n-gon, you associate some invariant Cn, so that limit of Cn as end up to be
Yeah.
end up to be pi, and the Cn will be something that Cn
Yeah,
will be
that-
analog of pi for regular n. That's what I think she's trying.
Okay, okay. Yeah, but if the polygon is inscribed and the polygon is circumscribed, we are approximating the area of the circle actually. So if we take as the invariant as the area of that object, so if we tend that to infinity, then that will convert to pi into some number. So then as a limiting case, we are getting pi. And if we take the unit circle, especially unit circle.
Yeah. So
Yeah.
she's asking what the
Yeah.
number Cn should be.
Yeah. Like dividing the radius. Or if we take the unit circle, then if we approximate its area, then we will get the pi namely.
And that's a good point.
Yeah, that's a good point.
Told that
Yes, sir.
there is something.
Area. Maybe area.
Okay, that's all. So let's thanks Ananya once again.
Thank you, sir. Thank you.
So by the way, I want to remark that next person please. So I want to remark that on Pi Day, it's our PhD students only who will spoke on Pi. Our experts are talking about other things, general mathematics, but it's our PhD students who have volunteered to speak about Pi. Okay. So once again, let's thank all four of them.
Mike.
So next speaker in this session is Nimish Kumar Mahabatra. Nimish is from number theory, where I find it either most or second most at So Nimish says, I think he is talking about constructibility of pi. So there is some concept called constructible numbers. Let's see what it is. Nimish.
Okay. So the title of the talk is constructibility of pi. Okay, so constructibility meaning that our usual high school geometry, that game of constructible numbers come actually. So in this game, we have these two instruments. So one is the compass. So you can always make a circle using that compass, and one straight edge. The straight edge is that worst ruler kind of thing, because that picture is not quite good. It has infinite length and only one side is smooth. Okay. So we have these two instruments, and we define whether a real number is constructible by this definition that it is and we always have given a unit length, and with reference to that unit length, we will decide which number is to be constructible or not, to decide that constructibility. So this straight edge is not our usual that scale where it contains markings and all. Okay. So a real number R is constructible if and only if given a line segment of unit length that I have already mentioned. We always have a predefined unit length, and a line segment of length, this mod R, can be constructed with compass and straight edge with finite number of steps. Okay, so this will be our definition for constructing a real number R. Okay. So we see this concept actually leads from some problems of geometry to solve via some using some concept of algebra. Okay. So let's see how this transformation works. So suppose S is the subset of R2. So I am taking here R2 because our construction in that usual geometry in that pen and paper, so it is all Cartesian plane we are talking about. So any set S we are taking as a subset of R2. So and at least two elements with integer coordinates we will take, and we say any point from R2 is constructible from that set S if at all this point can be obtained by a finite series of operation of the following steps. Okay. So these steps means we have the two instrument, we have a straight edge where we can draw a line, and we have a compass where we can draw a circle. Okay. So any point of intersection will get using these two tools will basically intersection of two lines, or it will be intersection of two circles, or it will be intersection of a line and a circle. Okay. So these are the only possibilities. So please look at the following equations, that known equations, that the equations of line actually it is represented y equal to mx plus c, and the equation of circle we have that x minus a whole square plus y minus b whole square equal to r square, with center at that point a comma b with radius r. Okay. So the key point here is to note that at worst the point of intersection of any two scenario means this intersection of lines or circle or circle line, at worst the point of intersection will satisfy a quadratic equations. Okay. So please keep in mind, this will come after something, after some slides after that picture, this quadratic. So now the question comes that how to add, subtract or multiply or divide two constructible numbers. Okay. So suppose a and b are given two constructible numbers. So in a number line, to find a plus b, we will just put our that compass at a where the length a ends, and in the right side you can mark up to b distance, the whole you will get that a plus b. And for a minus b, you have to just make the process reverse. You have to point your compass at b, and the left hand side you mark a, and the distance from a will give a minus b. But that product ab and a divided b, that will need some concept from the symmetry of triangles. Okay. So see that first picture, that triangle. So unit length is always given to me, so I can draw that a comma e, that means distance, and a comma b, that is also given because b is constructible, a also constructible. So I can make any angle alpha at that point e of distance a. I can join a line because I have a ruler, I can join, and again from that point b, I will just put my compass and I will find that point, that above that point d, where will it intersect. Okay. So you can see the small triangle, that ACE and ADB, they are actually symmetry. So if you find that ratio, that AE divided by AB, this should be equal to that A distance, and hence that DB comes to be that product AB. Okay. And similarly, reversing that process, you can obtain that A divided by B. Okay. So here that key is basically what we are doing, we are just constructing parallel lines to a given line and which is passing through some a given point. So this can be done using the two instruments. Okay. So we have these four operations we can do. Okay. So a and b, these are all integers, then we can construct all rationals, right? Because division, we know how to divide, how to find the distance a by b product. So we have all rationals are constructible. So now the question arises that whether only rational numbers are constructible or there are something more. Okay. So the answer is that if p is constructible, then square root of p is always constructible. Okay. So how to do this? So suppose p is constructible, meaning we have a length of p units. So we can always have, I can always have a line of p plus 1. I can take it as a diameter and just bisect that. You can get a center. You put your compass and make a half circle. This I can always do. And add one unit that from that right hand side to from D to B, and you take just one perpendicular. So that perpendicular it intersect at the point F. So now the distance that F B, that will be the distance square root of P. So whenever P is constructible, we can also construct that square root of P. Okay. So, and one more thing is here that these are basically the only operations we can do, that addition, subtraction, multiplication, division and extracting their square root. These are the only possible operations that can be done by these two instruments. So, whatever we observed, these are actually some basic facts from the field theory, that a number C is constructible, meaning it contains all the rationals, but it is strictly bigger than Q. Okay, because we can construct root 2 also, for example. Okay. Now, the theorem basically tells that this theorem, classified which real number can be constructed via these two instruments. So, the theorem is, if an element, real number this alpha is obtained from a subfield F of set of real numbers by a series of straight edge and compass construction, then the degree of this field extension F alpha over F has to be a power of 2. Okay. So, if you remember, I have told you that at worst a point of constructible numbers satisfy a polynomial of degree 2. Okay. So, this degree 2 is basically come into picture, and this is why there is 2 raised to the power k is occurring here. Okay. So, for example, square root of 2 is constructible, but cube root of 2 is not constructible, because the degree of extension of cube root of 2 over q, this degree is 3. Okay. So, the pi that previous speaker already told, that definitions of pi. So, this is basically the ratio of the circumference of a circle to its diameter. So, we have radius r circle, its diameter is 2r, we will denote it as d. So, pi is basically c by d. Okay. So, now we come to our main problem, that whether pi is constructible by means of these two instruments or not. So, this is basically called the squaring of a circle. So, this is a geometry problem actually posed by Greeks. So, the problems actually it tells that, is it possible using only straight edge and compass to construct a square whose area is precisely the area of a given circle? Okay. So, basically this question is equivalent to saying whether the square root of pi is constructible or not, or more basically whether pi is constructible or not. So, actually in 1882, Lindman actually proved that pi is transcendental. Okay. So, transcendental meaning it is not even algebraic. So, the degree of extension, it is not even finite, because we want to be constructible, it has to be some 2 to the power something, right? It has to be 2 to the power k, but here the degree is not even finite. So, this actually implies this pi is not constructible, and this shows a negative answer to the question, and it is impossible to squaring the circle by the help of straight edge and compass. So,
Are there any questions?
this one? Sorry? Okay, degree of extension? Okay.
Is a vector space over this
Yeah.
base?
I mean, you have a, so if you have done linear algebra course, then you think this F as Q, and you have a vector space FQ, you always have a basis. Okay, and the dimension of that basis, this is actually to the power. Yeah. Sorry. Yeah. This is in field theory. Basically, this question is viewed as a degree of the extension.
If it's a vector space over this space P, the dimension should be of the form 2 power. Any other question?
Sorry.
Go to the thank you slide.
Thank you, sir. This one? Yeah.
So, basically, we wanted to construct pi, right?
Yeah.
Constructibility of pi was right. So, why are we interested in the area of the square?
See, yeah, because if you have a unit circle, its area is how much? Pi. So now if I make a square with same area, so its side will be square root of pi. So actually it is equivalent whether I can construct pi or square root of pi. Okay, because if p is constructible, then square root of p is constructible. So that's why this problem is transferred to this. Yeah. Yes. Sorry? Oh, this is application of field theory. Yeah.
Okay. There are no further questions. Let's end. Our next talk will be by Malavika. She is speaking on series representations of pi.
Hi, Pi Day greetings to all. So here we are all familiar with the term infinite series, right? In some cases, it is really hard to find to what value this series is converging. But for some functions of pi, there are infinite series that converges to that function. In other words, there is infinite series expansion for some functions of pi. Some of those will be discussed in this talk. Let us start with a very basic polynomial function. So there are some details I am giving. It is a polynomial, and second thing is it has only 2 zeros. Okay. So with this details, how much we can identify this function? That is a question. So with these two details, we are factorizing f of x. So here it is given that 0 is a root of f of x. Therefore, when we factorize, x minus 0 will be a factor. And similarly, it is given that 1 is a root. Therefore, x minus 1 will be a factor of f of x. And the remaining term will be just a constant. Okay. Now, we already know the mathematical definition of pi, that it is the ratio of circumference of a circle to its diameter, which means whenever there is pi, there is a circle coming into the picture. So in order to get a series expansion for pi, we start with trigonometric function, because trigonometric functions are closely related to circles. So let me start with the sine function, and similar to what we have done in the previous case, I am asking the same question: what are the zeros of sine x? So that is the collection of all n pi's, where n is integer. Integer multiples of pi are the roots of sine function. Corresponding to each root, we are getting a factor. So I am factorizing the sine x as cx times 1 minus x square upon pi square times 1 minus x square upon 2 pi square, and so on. Here the first term x is corresponding to the factor 0, and the second term 1 minus x square upon pi square is corresponding to pi and minus pi, and so on. So opening these brackets, we can simplify it as c times x minus 1 upon pi square plus 1 upon 2 pi square plus etc. times x cube plus 1 upon pi times 2 pi the whole square plus 1 upon 2 pi times 3 pi the whole square plus etc. times x power 5, and so on. So here also we have to find the value of c. To find that, I am taking the derivative on both sides and evaluating it at the value at x is equal to 0. So here in the left hand side, the derivative of sin x is cos x, and evaluating at 0, we get it as cos 0, that is 1. And in the right hand side, except the first term, all the other terms are having powers of x, and therefore it is vanishing. Thus we can find the value of c, which is equal to 1. I am substituting back in the previous expression. Thus I can say that the sin x can be written as x minus 1 upon pi square plus 1 upon 2 pi the whole square plus etc. times x cube plus 1 upon pi times 2 pi the whole square plus 1 upon 2 pi times 3 pi the whole square plus etc. times x power 5 and so on. So this is the series expansion which we have found from our calculation, and by Taylor series expansion we have a expression for sin x which is given here, that is sin x is equal to x minus x cube upon 3 factorial plus x power 5 upon 5 factorial minus x power 7 upon 7 factorial and so on. So these are two different representation for the same function sin x. So now I am comparing the each coefficients which are given in two expressions. The first term is anyway x, and the second term I am comparing the coefficient of x cube. From the first expansion, I am getting 1 upon pi square plus 1 upon 2 pi the whole square plus etc. is from the series Taylor series expansion, it is 1 upon 3 factorial. On simplifying, what do we get? It is 1 upon 1 square plus 1 upon 2 square plus etc. is pi square by 6. It is in a very nice form. I can write it as summation 1 upon n square is pi square by 6, where n varies over the natural numbers. Let me define a function, zeta function for s greater than 1. It is the infinite series 1 upon n 1 square plus 1 upon 2 square plus, 1 upon 1 to the power s plus 1 upon 2 to the power s plus 1 upon 3 to the power s plus so on. That is termed as zeta of s. In short, series 1 to the power 1 upon 2 n to the power s, series over n varies from 1 to infinity, is termed as zeta of s. Actually, zeta function is it is of high research interest. The mathematician has done a lot of things on zeta, and the calculation what we have done now is giving one zeta value. Zeta of 2 is pi square upon 6. Some more particular values of zeta is mentioned here, that is zeta of 4 is pi to the power 4 upon 90, and zeta of 6 is pi to the power 6 upon 945, and zeta of 8 is pi to the power 8 upon 9450. So when if we see these values, we can have an observation that for each even positive integers that at which the zeta function is evaluated, it is taking a nice form, that is a rational multiple of pi to the power 2n. When zeta function is evaluated at 2n, zeta of 2n is a rational multiple of pi to the power 2n. But there is no similar compact form for zeta function to evaluate at odd numbers. With this, I am concluding my talk.
Any question?
All these series relate to pi.
Which series?
Like, we got the series for pi to the power 6, right? Like, can we get an explicit series for only pi?
Yes. One series, I think Anindya has given here, pi by 4. You are asking for the same method. No, we are getting for powers of pi. No. I mean, this question is still open now. People are researching on that. Yes.
Like while defining, first we defined as we consider polynomial whose roots are 0 and 1, and then we will define from there. Instead can be like say roots are suppose 0 and half, because kind of suppose periodic multiplication of log, and similarly can be defined similar way.
Yes. That was just to introduce the step I included the polynomial. That's all.
But just like once you know the roots, you can write out polynomial.
It was a simpler case, right? That's why.
So like you said, the zeros are 0 and 1. You put the polynomial to be c into x minus 1 into x. But we can take x minus 1 to be to any power, right?
I have mentioned that that is the only zeros.
There are no limited roots.
Yeah,
Oh,
that's right.
Yeah, those are like ramifications, counting multiplicity, not counting multiplicity. See, just wanted to illustrate that if you know all the roots, you can write the polynomial as a constant. And what Malvika also pointed, and you were asking the Lecture-2 and just 1. There is no such form known, and in fact, it is known that Lecture-3 is irrational, but Lecture-5 was irrational. No. See, that's what Anindya also mentioned, that what do you mean by explicit value of pi? So you can go up to certain decimal places and it has how you get to, right? Right. So that's what that Lecture-3 is irrational known, Lecture-5 we don't know. Then there are certain questions like if you take all the Lecture events, more or less what is unknown in there, that is pi square or pi power, let's say pi power. Everything else is rational number. Some similar thing we don't know about Lecture-3, Lecture-5, Lecture-7 and so on. In case some sequence or some function whose expansion includes all Lecture-1, Lecture-2, Lecture-3, Lecture-4.
No.
Huh? Yeah, I also doubt, but no, I think Veronica, what you are saying, certainly you are asking that some compact form where all these numbers comes, and these numbers already Lecture-3, Lecture-5, they are very mysterious, and you are asking that all they should appear in one compact form. So there is a lot of theory behind, extending these kind of things. But yeah, at this moment, let's say Lecture-2 and Lecture-2. Any more questions? Okay, let's thank Malvika again.
Thank you.
So our
Yes.
So our last speaker in this session is Cycle. Cycle was in operator quantum, right?
yes.
Quantum
Quantum
information. So
which is basically non-commutative program.
non-commutative. Okay, cycle. So you will talk about pi increasing probability. That is something I also did not know. That where does pi appear in probability, and that's why I requested cycle to talk. So cycle.
Hello. So today I talk about why pi occurs in, there's a lot of problems where pi occurs basically. So few of problem I will discuss, but there's a lot of problem like ballot problem, or like Anindo told that Buffon, bullet problem, that, and in particular I am telling about that basically that the normal distribution and the gamma distribution where pi occurs. So before going to details, I first tell the definition what is pi. Already our previous lecturer told all these things. So pi is basically that the that the circumference of circle and by divide by its diameter, or the area of circle by square divide by its square radius. So now I little bit talk about why the number pi is represent as this symbol. So why the Greek symbol arise basically? In 1706, the English mathematician William Jones first, when they are calculating the ratio of that number, then they use that the representation of pi. First they introduce these things, and after that, the Euler, where probably that the transcendental number where Euler proved these things, that Euler used in mathematics the pi representation. After that, the George used in probability, and after that in mathematics pi comes regular basis. Then that the notion, that the symbol. So now we go to the normal distribution. Why? So you guys know most of the people know that what is the distribution. Yes? The third year and fourth year guys? You know the distribution function? Maybe second year and the first year, maybe for that I just write down that what is the distribution function. Maybe I skip this one because I will tell later what is the distribution function, but at least if you know that the probability, if x is a random variable, then the probability distribution function is basically at a point, it's the probability of that event happen. Yes. So in standard normal distribution, why that the square root 2 pi comes? Yes? Sorry? The distribution function is defined by density function basically. This is the density function. Yes? Yes. Yes, yes, from 0 to some variable, yes. So why that the pi is in density function? So the question is, so answer is, so if density function, then whatever the area under this curve, it is 1. So if it's not that the scalars come, so then function becomes basically that the e to the power minus x square by 2, which graphs looks like this kind of bell curve. Yes? So if you calculate that the area of this under this bell curve, it's come basically for that. So if you scaling with by 2, then it's come the square root 2 pi. So anyone asks why I write this expression only? Yes. Basically normalize. That's why, because you have to ultimately have to come that the unity. So before going to the finding the area of this curve, so we go to one motion, that is the factorization. We know that what is factorization? 1 factorial, 2 factorial, 3 factorial. Can anyone tell that the factorization of the fractional number, that is 1 by 2, 1 by n, or 1 by 4? Yes? So if we draw the graph, that 1 is 1, 2 2 is 2, 3 is 6 and 4 is 24. So the graph looks like this, yes, and if you see that this graph is quite first of all smooth, that is differentiable every point. You know the derivative first year and second years twice, so it is infinitely differentiable and it is smooth and it satisfied that g of x plus 1 equal to x gx and ln of log x basically it becomes convex if you draw that ln of that the gx function. Yes, so it is seen that the only function satisfies these three property is the gamma function, which is looks like that the gamma x equal to 0 to infinity e to the power x minus 1 e to the power minus t dt. So from here, so what we get basically that the x factorial basically gamma of x plus 1. So if we calculate that the half factorial, so basically what gamma of half plus 1. So basically what comes down, that is 0 to infinity e to the power x minus x is half plus 1 minus 1 and e to the power minus t. So if you okay, e to the power square root t yes. So this is the function, but here is interesting thing is if we calculate the only gamma half, then it's become half into gamma half, because we know that the function satisfied gamma of x plus 1 is x gamma x. So if we put x to be here, so gamma by 3 by 2 basically the 3 half factorial is half gamma half. So what is gamma half? This is 0 to infinity t to the power half minus 1 e to the power minus t dt, which is basically if you use the change of variable things, that is t equal to basically x square, then this becomes this is minus infinity e to the power minus x square dx. So what the function has the one kind of normal distribution has, and the area of that we wanted to calculate. So direct calculating this area, it is little difficult, area under. So what we do, it is seen that if we instead of doing there is a single variable, if we have a cousin problem like if we have the find out the area of the curve e to the power minus x square plus y square dx dy, it is little more easier than direct calculating e to the power minus x square. So the bulk surface become, if you have this axis, then the Bell surface become this. So if you basically you know the integration that the basically sum of that area, all these kind of cylinders, or even for 2 dimension basically all these kind of strip, if you add, then you get the area of the for this curve, and for the volume basically all possible adding areas, you get the area of the volume. So if you get one of the cylinder out, yes, then this is a circle, yes, and these coordinates are basically x and y, where z is fixed. So basically what's come, that if you have it in a 2 dimensions space, if you take a coordinate x and y, which is this is x and this is y, and then using Pythagoras theorem, that this is r basically square root of x square plus y square, yes. Now you have that circle of radius r. So what will be the area of this surface, that this cylinder? Second year guys, you are doing that the several variable calculus, and rest of the people also did. So can you tell what is the area? So if you cut down this cylinder, then it's become what? So which is basically this is the length and this is the perimeter or circumference of the circle. So we know what is the circumference of the circle. So what is the circumference of the circle? 2 pi r. This is 2 pi r basically. And this is the height of the, because if you take any point from here, so it is belongs to that curve, and it is basically e to the power minus x square plus x y square. So it is comes down, becomes the length is basically this. So that means length is e to the power minus r square. So what is? That is the circumference and the height of this curve. So that means the area of under this curve is that is 2 pi r e to the power minus r square. If you take small thick of this surface, then it's become volume. So if you integrated this one, because there is a lot of this minus infinity to the infinity, minus infinity to infinity, this one, if you integrate all these things, you get that the area 2 pi r dr. Yes. Now the if you comes out pi, now this function has an antiderivative, because previously when it, yes, okay, sorry, yes, from center to 0 to infinity, yes, sorry, thank you. So this has a primitive. So you know that the several that the calculus of first, that is basically minus e to the power r square 0 to infinity, and which is basically pi. Yes. So what comes down, that minus infinity to infinity e to the power minus x square plus y square dx dy is the area of the basically circle. So now we have to show that these things, anything, x square minus y square dx dy equal to basically dx whole square means multiply with 2 times. So now what is this? This is minus infinity to infinity e to the power minus x square dx, and which is independent of y. So it comes out so now you get the result that so we get the desired result that integration of whole square is basically pi. So now if you see that one thing that there are lot of bell curve something like fx equal to 1 by 1 plus x square, this also has a area which is related to pi, because if you integrate this one minus infinity to infinity this is the tan inverse x. So my motivation in this talk is that there is lot of bell curves where the area is related to pi. So this how the area under the bell curve this pi has comes into that picture. Thank you.
Okay guys, any question? No? Okay, let's thank Saket once again. Alright, so we have a cup of tea now and then we assemble again at 4. But lecture at 4 o'clock, that is quantum talk 2 is in first floor. Okay, it's not in ground floor. Okay, let's go for a cup of tea. Like that?
Yes.
The Wallis product approximation of pi, and suppose I take 6 into sigma 1 by x squared and take a square root. This like approximation